I want to talk about energy transformations and then the molecule ATP and its role in energy transformations in living things. So here's the molecule ATP. We'll look at that in a little bit more detail later. And here's some energy transformations, right? So light energy captured by plants through photosynthesis, taken and converted into organic molecules, which are then burned for energy in the mitochondria, which produces the molecule ATP, which powers cell work, etc., etc. So before we get into the details of ATP, we need to talk about energy and energy transformations. So some energy transformations are what are said to be exergonic. And exergonic means energy releasing. So this diagram here on the left, the red one, we can see that we have high energy waste products, high energy reactants, and they're reacting to produce low energy products. So taking food and burning it is an example of an exergonic reaction. That's going to release energy, whereas over here on the right we have low energy reactants producing high energy waste products, or high energy products, not necessarily waste. An example there would be photosynthesis, where we take carbon dioxide and carbon dioxide and water and produce high energy glucose and oxygen as a waste product. So to talk about energy and energy transformations, there's a term now that we've introduced into AP biology, which is called free energy. Free energy is just any form of energy. It could be light energy, could be chemical energy, could be heat energy, could be electrical energy, okay? And energy transformations involve changing from one form to another. Most of the free energy we're going to talk about is in the form of chemical energy. So those chemical energy transformations can involve high energy reactants producing low energy products, and that means that there is a loss in free energy within those molecules. So that means that the change in free energy, which we're going to call G, delta G, is going to be negative. So anytime we release energy from molecules, we have a negative G. We're losing free energy within those molecules. Whereas when photosynthesis, we take low energy carbon dioxide and water molecules and produce high energy sugars and oxygen, we have an increase in energy. We're storing more energy in those products. So that's an example of a positive G. So again, if delta G, the change in free energy, is less than 0, that means it's exergonic. That means we're releasing energy from those molecules, and that's going to result in an increase in entropy, and we'll talk about what entropy is in a minute. If the change in G, delta G, is greater than 0, that means that it's a endergonic, or energy storing reaction, and that's going to decrease in entropy. Okay, so now let's get to this entropy thing. First off, energy transformations, we have to talk about two laws of thermodynamics and need to kind of have a basic understanding of these to understand energy transformations. So the first law, you can see in the diagram, we've got chemical energy, we've got electrical energy, we've got kinetic energy, we have electrical, mechanical, chemical, all these different forms of energy, and they can transform, right? So we know that energy can be converted from one form to another. Power plants burn fossil fuels, chemical energy, to produce electricity. Then we can convert that electricity into light, or into sound and light and music and whatever. Okay, so first law of thermodynamics basically says that energy can be transferred from one form to another, or transformed from one form to another, but it cannot be created or destroyed. So we know that all energy powering all life on Earth comes either directly or indirectly from the sun, and then it's transformed into different forms, and ultimately it's radiated back out from the Earth as heat, right? So energy coming in as light, being radiated out as heat. Well, that gets to our second law of thermodynamics. So in these energy transformations, energy, when it's transformed, we lose a lot of that energy. We don't really lose it, but we convert it to less useful forms. And this is really what the law of entropy is about. Entropy is basically systems tend to go from order to disorder, right? So if you didn't maintain your house over 100 years, 500 years, it would fall apart to the ground. It wouldn't just keep building up and getting highly organized and more complex and nicer, right? It would just kind of go into disorder and chaos. So this is really what entropy is saying. In each energy transformation, we're losing some of that energy into entropy. Okay, well, what does that mean? That means that basically every energy transformation, we lose energy in the form of waste heat. So we talked about this in terms of ecology and food moving through trophic levels and energy flowing through trophic levels, and the fact that we lost a lot of the heat at each trophic level. So something that you see there. The last thing I want to talk about is when we take chemical energy and convert it into energy for work, we also produce this molecule ATP. So now let's talk about ATP. This is what it looks like if you had to build a molecular diagram with the oxygens and the phosphorus. These are 3 phosphates attached to a ribose sugar attached to an adenine. So let's look at those in a little bit more detail. So here's ATP, and you can see adenine. This is basically just one of the nitrogen bases, right? It's the A that usually pairs with a T in DNA, right? And it's attached to a ribose sugar, just like an RNA nucleotide, okay? It's a 5-carbon sugar, and that's attached to 3 phosphate groups, okay? So the adenine and the ribose are not that important in this molecule. They make up a molecule called adenosine. So it's adenosine triphosphate, but it's really in the triphosphates that we have the importance of ATP. If we look at them, we notice all these oxygens are surrounding each other. They're very electronegative. They don't like being around other negatively charged things, right? They want to get away from all that negativity there. So if we break a bond between, let's say, the 2nd and 3rd phosphate, we can produce a lot of energy, okay? And that's what we can use in our cells to do all cell activities. So how do we break that bond? Well, again, that's a hydrolysis reaction, right? So we take hydrolysis means splitting water. Take a water molecule, stick a hydrogen on one and a OH group on the other, and we have released some energy and produced a molecule called adenosine diphosphate, 2 phosphates on there instead of 3, and a little bit of energy, which we can then use for cell activities. Okay, so here's the ATP cycle, right? Energy from catabolism. Catabolism basically means breaking down big molecules into smaller molecules, and these are typically exergonic, energy-releasing reactions. And instead of just converting that into waste heat like you did in the calorie lab where you burned the food, we're going to actually capture a lot of that energy and store it in this molecule of ATP. And then that molecule is going to be used for all cell activities. So why do we have to do this in our cells? Again, you can think of like a molecule of glucose as like a $20 bill. And most cell processes are maybe like 50 cents, 75 cents. You need smaller units of energy. So we're going to break that big molecule, that big stored energy, into smaller molecules. So we say ATP is the energy currency of the cell. It's a smaller, more usable form of energy that we can use for all cell processes. And when we use it for cell work, it's going to release that energy and produce these low energy products. Again, exergonic reaction, breaking this higher energy molecule into lower energy molecule and using that energy for cell work. So an energy transformation. So the last thing we need to talk about is how and why we can release energy by burning food in our cells and how that works. So again, on the periodic table, remember we talked about water and we talked about oxygen and hydrogen. We talked about how oxygen is very electronegative, hydrogen is weakly electronegative. So things over here that really, really want electrons are called oxidizers. They accept electrons. Things over here that give up electrons are reducers. They will give up their electrons to oxidizers, okay? And this is important because when electrons are passed to an oxidizer and they're close to that nucleus of that oxidizer, they're in a very low energy configuration. When they're being held by these reducers, they're in a high energy state. So we can actually transfer energy by moving electrons from reducers to oxidizers. And that's what we do when we burn our food. We're really just oxidizing our food. We're taking those electrons from the food molecules and we're transferring them to oxygen. So let's look at how that works. So oxidation basically just means losing of electrons, and reduction means gaining of electrons. Hopefully you remember that from chemistry, right? And then in chemistry you probably have to remember a diagram that looks something like this. You've got a reducing agent that has electrons and you have an oxidizing agent that wants those electrons, you know, like oxygen, right? And what happens is the oxidizer is going to take them from the reducer, and the oxidizer is going to get reduced and the reducer is going to get oxidized. It's going to give up its electrons, right? So we have a reducing agent giving up electrons, and we have an oxidizing agent accepting electrons. And by doing that, this is now, some of the energy from this has been transferred to this. So this could be, for an example, calcium, which has a valence of +2. This could be oxygen, which has a valence of -2, right? And what we would get is calcium oxide, where the oxygen now has those 2 extra electrons. So this is basically what happens in ionic bonding, okay? All right. Now let's look at organic molecules. So organic molecules, it's not really a passing of electrons. What it is when these reactions occur, electrons are being moved from reducing compounds closer to highly electronegative compounds, oxygen, okay? So when those electrons are closer to an oxygen, the nucleus of an oxygen, they're in a very low energy stable configuration. When they're in these carbon-hydrogen electron shells, they're in very high energy, reduced energy configurations. So we can think about this as sort of kinetic energy. Notice these guys are farther away from the nucleus. And when we combine them with oxygen, now they are right next to the oxygen. These guys now are right next to the oxygen. So what we've done is we've taken these high energy electrons and we've oxidized them by moving them closer to a strongly electronegative atom. And by doing that, we've released a lot of energy. So the reducing agent, in this case methane, is providing high energy electrons. The oxidizing agent, which is oxygen, oxygen is always the oxidizer, it's easy to remember, is accepting electrons into a lower energy configuration. So it's basically, you can think about them as like taking the potential energy and converting it into a, using that potential energy and releasing that potential energy and storing it in a low energy configuration. So that's basically how redox reactions work with organic molecules. We're not donating from one to another, but we're moving electrons closer to oxygen where they're in a low energy state and away from these high energy reduced conditions that exist with carbon and hydrogen. And that's it.